Hi, my name is Josh Nabathilan, and I was the reporter for Group 2 of the Rankine cycle experiment. Now, quick overview, we're going to talk about the Rankine cycle itself, the equipment, the data we got, and the calculations, and this is a quick summary. Now, the Rankine cycle, this is the ideal Rankine cycle. It undergoes from steps 1 to 2, it goes an isentropic pressure increase, usually by a pump. And then from step 2 to 3, an isobaric heat addition from a boiler, usually. Then step 3 to 4, which is isentropic pressure loss from a turbine to get work out. And isobaric process from 4 to 1, which is to condense it, the working fluid. This is the equipment. We've gone over it several times already, so I'm just going to skip it. Now, this is the data we got. This is the fuel flow over time of the propane to fuel the boiler. And this is the boiler temperature. This is the boiler pressure versus time. I was in charge of managing the pressure, but I kind of had a hard time trying to maintain it at 110 psi. This is the inlet versus outlet pressure over time of the turbine. And this is the temperature of the turbine, inlet and outlet. This is the current we got from the generator that was connected to the turbine. And this was the voltage we got out of the generator itself. We were supposed to maintain it at 6 volts, but yeah, I was having trouble with that. And this is the turbine RPM over time. Now, the lab manual states that we should, for our calculations, we should get a piece of data at a certain specific time that met the steady state requirements, which were stated to be 110 psi in the boiler, and we had an output voltage of 6 volts. So I chose a data time 33 seconds, and this is the data, and this is the properties that came at that specific time. And this is some steam table data of the different stages of the Rankine cycle. We had to just interpolate that, and for fun, I just decided to do it in English units because I don't know why. So this is the boiler heat flow. We ignored the work out of the boiler because there's no work, and we ignored kinetic energy and potential energy. So it's just the change in enthalpy. The change in enthalpy is when at H3 is the boiler at 110 psi. I forgot the temperature, it was in the list. And H2 is the enthalpy of the water at atmospheric pressure and room temperature. And when we got the difference, we got 1158.658 ATU per pound. I got specific heat. And then to get the turbine work rate, there was a huge pressure drop between the turbine inlet and the boiler outlet. So I had to use the properties at the turbine inlet instead of the boiler pressure outlet, which the enthalpy there is 1168, and the enthalpy in the exit of the turbine is 1159. Once we get the difference and we multiply that by the mass flow rate, we got a work of 0.0629 BTU per second. Again, English units. So to calculate the mass flow rate, we just took the amount boiled and then multiplied that, the volume boiled, multiplied that by the density of the water over the time of the experiment, which was 547 seconds. So we got a mass flow rate of 0.00684 pounds per second. Now for the generator efficiency, it also, in the list of data, it also stated the power that came out of the generator. So at 33 seconds, the generator was producing 5.45 watts, which was 0.00517 BTU per second. And then to get the generator efficiency, I took the power from it, divided it by the turbine work, and multiplied it by 100, which we got an 8% efficiency from the generator. Now for the condenser, I took the turbine exit properties, and it's the difference in enthalpy for the turbine exit properties as well as the exit properties of the condenser, which was undergoing a phase change, which was somewhere on the saturation line here. I took the point in the saturation line by getting my value of x, which was the amount of steam over in volume over the amount total boiled, which was here. And then, yeah, something like that. And I got the enthalpy for that point in the phase change, which I got a condenser heat flow of 198.24 BTU per pound. And then the efficiency of the condenser is just the amount that was condensed over the amount total boiled times 100%, which was 16.76%. Now, thermal efficiency of the whole cycle is 100 times the work of the turbine over the heat it took to create that work. Usually, it would be the work of the turbine minus with the work of the pump, but in this case, we don't have a pump, so it was just the work of the turbine, which we got 0.793%. As you can see, that's a pretty terrible efficiency, but that was because of the pressure drop between the turbine inlet, and the boiler pressure exit, and it's also because we didn't pump back any of the condensed fluid into the boiler, so it was an open system, not a closed system. Now, loading increases the amount of work the turbine has to do to turn the generator. We load the turbine so that we won't destroy the ball bearings on the bearings on the turbine in the experiment, and it also decreases the output voltage. And in summary, the Rankine cycle is an important process used to produce most of the world's electric power. And this is my references. That's it. Any questions?